How's that going? So far so good. Not too terrible. I'm hoping. Okay. You had a question about the homework? Yes.
Yeah, how many iterations?
How many?
Until like hundreds?
Yeah, I don't know, 5, 6 iterations. I mean, you could do a bunch, but you know, at a certain point, what happens on the graph gets really tiny, right? And you can't really see what's going on. Okay.
Can I do it as much as I want?
I'm sorry.
Can I do it as much as I want?
Yeah, you can do it as much as you want. Yeah, that's fine. No penalties for that. I'm gonna post homework 7, or not homework 7, homework 5 soon. Okay, and I'm posting it. I'm gonna try to post it early, just so you guys have as much time to work on it as possible. It's a little bit of a longer one, and you know. It's to get into this idea of statistical simulation. Okay, so I'll explain probably on Wednesday, but you'll be simulating a game of Monopoly. The board, just the board movement. Okay, you don't have to implement buying strategies and trading strategies and things like that. Okay, just board movement, but it's at least complex enough that I think it'll give you just an idea of how some of this stuff works. And I did it in the past. A lot of students struggled with it, so I'm going to give you some starting code I'm hoping to help guide you. And of course, if you do or don't want to use the code, that's up to you. But I think my starting code outline is a good starting spot. So we'll talk about that, but that will go up probably tonight. Okay, so today I want to talk about coordinate descent. And this is part of your homework. This is an optimization algorithm. Okay, and it's multi-dimensional. Oops. Sorry, something just happened here. Okay, multi-dimensional. Okay. All right, and so the idea is, let's say you have some in 3D space here. You've got some kind of, just imagine this mesh bowl here or something, okay? And you want to find the minimum here. So this will be x and y and z or something like that, okay? And so we can create a contour. And this would look something like this. Okay, and this is not a very good example. Let me make this a little bit more like this. Okay, so we'll pretend that that our contour looks something like this. Okay, and so the way coordinate descent goes is we want to minimize some function f, which is a function of x and y, right? So f of x and y is equal to z, and we want to find the x and y that minimize this function. Okay, so the way this is going to work is first, and the algorithm is basically this. Okay, so have an initial x and initial y. And then, set y equal to, we'll say y sub 0, and then, so now you have f of x, y is now just a function of x. So this is the idea. So you're setting y equal to y sub 0, okay? And that, because this is now just a constant, this joint function, the function of x and y, just simplifies to being a function of just x only. Okay? And so you have this, and so you so minimize this, you know, f of x, where y is equal to y0. Okay? So minimize that function, okay? And use and update x. Okay? So I guess this will be x at x sub 1, okay? And then now set x equal to x sub 1, and now you have f where x is equal to x sub 1 is now a function of y. Okay, so this is now a function of y, and minimize this function, finding the y minimize this function of y, and then you iterate. So now you're going to set y equal to y1, and then dot 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 iterate until convergence. Does the idea there make sense? Are there any questions? So what this looks like is, you know, you start off, let's say you start off right here. This is going to be our point x0 and y0. Okay? And so what you're going to do is you say, we're going to have y equal to y0. So just searching along this path, so this is where y is equal to y0, and we're just, because this is set here, we're going to find the x that minimizes this. So maybe that goes right here, okay? So this is f of x is minimized here. Okay? And then, so the next iteration, you search along where, this is now where x is equal to x1, and then you say, oh, it's minimized right here, okay? So minimized. Okay, and then, so now searching along where y is now set to here, you find this, and you say, oh, okay, it's minimized here, and you just kind of keep going back and forth, one coordinate at a time, as we until at some point you end up here. And so on this kind of thing, you're going to end up with a kind of this stair-step pattern to get to the minimum point there. Okay, and so when you do your homework, right, you just have to re-express your function. So you're going to have to say, if I set y equal to something, you know, can I turn this into a function of just x, and then can I turn this into a function of just y? Okay, and you'll need those two functions because those are the functions that you're going to plug into your minimization algorithm. Okay, so basically we're turning the multidimensional minimization algorithm into a series of unidimensional minimization algorithms, right? And for the unidimensional ones, you can use any algorithm that you want, the golden section search method works well because you don't have to worry about taking derivatives or anything like that. You just kind of throw in the thing, and as long as you can calculate values of the function, then you can get a minimum. So I don't know, let's say you have f of xy is equal to, I don't know, y cubed plus xy squared plus x squared y plus x cubed, or something like this. Okay, I'm just making this up. Right? Okay, and then so basically you'd say so in your algorithm you'd say, okay, we're going to set y equal to y0, okay, and then so your f of xy becomes, and you know what, this is not going to have a single, let me throw in x to the fourth and I don't know, a y to the fourth term also, and I think this will make it concave up. Okay. Okay, so f of xy, if you set y equal to 0, then basically you really just have you know, just the x terms to worry about, right? So this becomes you know, y sub 0 cubed plus xy0 squared plus x squared, you know, y0 plus x cubed plus 2x to the fourth plus 2 y0 to the fourth, okay? And so this is now a function of x. And we can plug this into, you know, our golden section search if we want. And we'll just do golden f of x, and then we give it some kind of range, you know, minus 1,000 to 1,000 or something like that, okay? And it's going to run through this thing, and it's going to say, you know, update, you know, x sub 1 to be, I don't know, 0 or 2 or I don't know, okay? Just some value, right? Whatever this is, okay? And then you take that and you plug that in and you plug that back into here, and now you get it f sub y, and then so this is going to be just a function of y, and this will be x sub 1 y squared plus x1 squared y plus x1 cubed plus 2x1 to the fourth plus 2y to the fourth, okay? Okay, so, you know, in our code, you're going to want to say, you know, f sub x is some function of x, and then basically you can probably just put all of this here. You can probably just write y to the third plus x y squared, etc., etc., etc. And because of our scoping rules, as long as you have y set somewhere else in the environment, you know, it's going to take the value for x and plug that in here, but it will search the rest of the environment for the y. Okay? So because of our scoping rules, it will search the environment for y. Okay. And then you'll need another function, f sub y, and this is going to be a function of y, and it's pretty much also going to be the exact same thing as over here, but you're now saying that this is just a function of y. Okay, and again, because of our scoping rules, it will search the environment for the values of x. Okay, so this will still be y to the third plus, you know, x, y squared, etc., etc., etc. Okay. So I can demonstrate how this might work if you wanted to do maximum likelihood estimation or something like that. Okay. So we'll just start off with a very simple example. Is this okay? You guys got all this down? All right. So let's say we want to do. Let's say we have some normal model. Okay. Normal model with a mu and a sigma. Okay. And then so our data has come from this, right? So we have data coming from this normal model. And what we want to do is we want to find mu hat and estimates of mu and sigma that maximize the likelihood of our data. Okay, that's what we want to do. So, the normal model, this produces, you can look at the normal density, okay, which is, I don't know, e to the whatever. It's kind of a mess, right? But in R, we have a function that gives us the normal density, right? So first of all, let me just talk about what our likelihood function is, right? So our likelihood function, likelihood of the data, is going to be the product of all the, the density of each, the probability value, probability density of each data point. Right, so we can, is this okay with everybody? So all we're doing is we're just going to find, so if we were to write this as a function, it would just be the probability of x given mu and y, where p is the normal density. And in R, this is simple, right? What is the function that we use to find the normal density in R? Not p-norm. P-norm is the cumulative density, cumulative distribution function. It's d-norm, right? D-norm x, and then you have mean equal to mu and sigma, or standard deviation s equal to sigma. Oh, what did I write here? I wrote mu and sigma and y. This should be mu and sigma. I apologize. Okay. D norm, is that okay with everybody? So D norm is the one that gives us our the probability density. That you go to Wikipedia and you look up normal distribution and it has a little bit of the mess. Okay, and then so we would do this, and then we would need to do the product of all of this, right? We would have to tell R to multiply all of these together. The only problem here is that let's say the mean was 100, and we have a value, our current estimate of the mean is, I don't know, 100, and we have values out at like 200, and we have a small standard deviation. Okay, basically this d norm is going to give us a value so close to 0 that R is going to treat it as 0, right? Because we have finite decimal precision, it's going to treat it as 0. Mathematically, it wouldn't be a problem, but computationally, this becomes a problem when values are so close to 0 that R can't differentiate it from 0. So what we want to do is we're going to take the log of this instead. And that's going to take a very small number and turn it into just a very negative number. And then we can add that up, right? And so So because the log function is what we call monotonic, meaning that it's, it increases, and it's always increasing. There's always a positive slope to it. That means when we find the maximum, the value that maximizes the log, it will be the same value that maximizes the product. Okay? So, the log, or natural log, is monotonic. So the value that maximizes this will maximize the original function. Okay, and so luckily for us, in R, we have d norm, and then, we would do x, and then the mean is, mu, and s is the sigma, and then there's also log equals true. And if you say log is true, then it will return the log of the normal probability, and then you can turn it, instead of a product, you would now have a sum. Okay, and so the log likelihood would be the sum of all of this. Okay, so let me just I have some code to demo this. I'll actually, let me upload it to CCLE for you guys. Oh, that didn't work. Okay. All right, let's get this open. Okay, so I'm here. I have the let me console on the right here. So I have the golden section search function from before. This was covered on Friday. Okay, so here I'm going to just generate a bunch of data. Set seed, I'm going to just generate a bunch of 1,000 points coming from a normal distribution with a mean of 10 and standard deviation of 150. Okay, I could change this to, okay, we'll just start off with this. Mean is 10, standard deviation is 150. So I can just do a histogram of our data right now. Did something happen? Figure margin's too large. Oh, yeah, well, that happens when you have a... Okay, so it looks kind of like this, just offset a little bit, right? Okay, so here, for the likelihood function that we want to minimize, all I'm doing is I'm saying take the normal density, d norm, of our data, okay, where mean is equal to x, which is, because we're taking, this is going to be a likelihood function based on mu, okay, where the mean is equal to something. So right now I could just plug in mean is 0 and our standard deviation is equal to 10, right? If these were my current estimates or something, or mean is 0 and standard deviation is 1, and I would use log is equal to true, and it's going to tell me all of these numbers. It's going to give me like negative 2,000 something, right? And then the total likelihood of this would be the sum of all of this, and I would want to maximize this value, right? So right now my log likelihood is huge. Because the golden section search function is a minimizing function and we want to maximize, we're going to multiply this thing by 1, negative 1. okay? And so we're going to minimize this, but this will give us the maximum, right? Okay, so here I have the likelihood function as a function of mu, and it's saying it's a function of x, and I'm going to take x and plug that into where the mean is, and it's going to use our value of sigma using scoping rules. It's going to take the value 1 right now, okay? We're going to do the same thing over here. We're going to take, now it's a function of sigma, so mu, the mean is going to be the current value of mu, and it's a function of x. X gets plugged into here for where the standard deviation is. Okay, so I have a function, I've turned our likelihood functions into a function of one variable and a function of another variable. Is this okay with everybody? So here I can say, you know, what is the total likelihood of our data? Okay, again, our data is stored here. I can say, what is the total likelihood if I used the estimate of 100 as our mean? Whoops. Oh. I need to set those things here. Okay. So what is, you know, this is the likelihood if mu is that. This is negative of that. Okay. If I used mu as 1, it's a different value, and if I put it in 10, it's another value. And we want to minimize this. Okay. And so what I'm going to do is I'm going to just run the golden section search on this. I'm going to say, do your search from -1,000 to 1,000, okay? And let's update our value of mu, okay? So currently, our value of mu is 0, and we're going to say, run the search on this. And after doing the search, our estimate of mu is 8.252777, okay? And so now we're going to use that to update our value of sigma. Right now our value of sigma is 1. We're going to tell the golden section search to search on the range 1e to the -10 to 1,000, right? Sigma has to be a positive number, so I can't go from the negative range to positive range. So I'm going to just say, you know, search this entire thing. And I do that, and it updates sigma to 155. Okay, so this already, just after one iteration, it has brought us in very close to kind of the values we use to generate our thing. Okay, and then basically I would just iterate going back and forth. I would run this again. I would say, okay, give me update mu again, just running this. So I would iterate this, and what is my updated mu? And it has just changed ever so slightly. Okay. And I say, okay, well, using that, update my sigma, and my sigma didn't change at all, okay? And we're like, okay, well, does this mean it has converged? Maybe, okay? We could run through a few more iterations to see, you know, if it truly has converged. I could do like for, you know, I in 1 through 10 and just see if, what's going on here? Just see if anything changes, and it probably won't, okay? Because for this, it's exactly the same. And we can look at our data itself, right? And we can see, you know, what is the maximum likelihood of the, you know, our data. So we'll just say, you know, what is the mean of our data? The mean of our data, well, what do you know? It's pretty darn close to what our estimates are producing, right? And we can ask, what's the standard deviation of our data? Okay, and it's also very close to what we have. So our maximum likelihood estimates are honing in right to what our data is saying. Okay, as far as that goes. Okay, and it really got, for our normal distribution, it got in there really quickly, right? Like after 2 iterations, it zeroed in. Okay, we can try this again. I could say, you know, let's make the mean 1,000 and the standard deviation equal to 5. Oh, you know what? Let's not do 1,000 because we'll say 900. Okay, so we'll just generate new data, starting off with our initial estimates will be mu is 0 and sigma is 1, and I'll just do one iteration at a time. So after one update, my estimate of mu is already very close to 900. Okay, my current estimate of sigma is 1. I'm going to just do one iteration of this, and now my estimate of sigma is right around 5. Okay, and I can just do a few more iterations and see if that really changes anything. And it doesn't, but it's given us pretty good estimates of what our probably the mean of our data is. The mean of our data is right there, and the standard deviation of our data is also very close. Okay. So okay, and so even though the normal distribution that generates this because of random variation, we're getting something a little bit different. Okay, is this okay as to far as how the coordinate descent algorithm works? You're taking you have this multi-dimensional function, right? And you're just updating one variable at a time. You're going to keep all of the other variables constant, and so it becomes just a function of one variable, and you're going to say, I'm going to change, try to find the value of that one variable that minimizes this current one variable function. And then you just cycle through each of these things. Okay. This can be used to do least linear regression. Okay, so if you think of what linear regression is, the best fit line in linear regression, what is that? It's the line that minimizes sum of squares residuals, right? So you can turn you can create a function as to a function of the sum of squares residuals and say, I want to minimize, I want to find the slope and I want to find the intercept that's going to minimize the sum of squares residuals. Okay, so that's what I've done here. Here I'm just generating some data here. Okay, and so here we want to find the line that's going to minimize the sum of squares residuals of this thing. So linear model in R will do this very quickly, and we can see that the slope and the intercept that's going to minimize the sum of squares residuals will be this and this. Okay, which aligns what we kind of use to generate our data here. Okay. Okay, so if we think about what the sum of squares residuals is, okay, it's really just we're going to find values of y hat. We would do intercept plus slope times x. Okay, that's going to be what our estimates are. And then the residuals would be y minus y hat. And the sum of squares residuals is we would square those residuals and get the sum of squares back. Okay, and so here I'm just doing, I have the function that's going to return sum of squares residuals as a function of the slope. Okay, and here I have pretty much the exact same thing, and this is sum of squares residuals as a function of the intercept. Okay, and right now I have slope is 0 and intercept is 0. Okay, now what we're going to see is that it's going to take us a ton of iterations to get to the actual thing. Okay, whereas with the normal distribution, it zeroed in on the values very quickly. Okay, so what's kind of, if we were able to plot the f of x and y, so this was f of mu and sigma for the likelihood of the normal, it looks kind of like this. Okay, and so when we start over here, it's going to go along here and it's going to say, oh, it's minimized here, and then it's going to go up here and it's going to say, I found the middle really quickly. Okay, with my sum of squares thing, what's going on is we've got this very, very, very narrow thing like this. Okay, it looks something like this. Okay, it's kind of like this razor thin contour. Okay, and so what it's going to do is, as it's searching, it's going to say, okay, I'm going to go over here, and then I'm going to go up here, and then I'm going to go over here, and then I'm going to go up here, and then it just has to keep doing this tiny little zigzag dance all the way until it gets into the middle here. Okay, so it's going to take many, many, many iterations because the shape of this contour thing doesn't lend itself very nicely to kind of this 90-degree only thing. Okay, but it still works, and it will get there. It's going to take a little bit longer. Okay, so again, we're just trying to think, what is the function we're trying to minimize? It's the sum of squares function. So I'm going to start off with a slope and an intercept. The sum of squares as a function of the slope, the sum of squares as a function of the intercept. Okay, and I'm going to just say, do some iterations. And here we're just using the golden section search, a unidimensional optimization thing on the function that minimizes on the function as a function of the slope and a function of the intercept, and we're just going to iterate through these things. Okay, so just after 1 iterations, it has updated my slope to 2.3 and my intercept to negative 0.5, where in truth the slope is 8 and the intercept is negative 400. Okay, and I can just run one more iteration, and so my slope is now 2.312 and my intercept is now negative 1.16. Okay, so it's getting there, but we can see it's moving a lot more slowly. Okay, we don't have this rapid convergence like we did with the normal thing. Okay, so I'm going to just run 5,000 iterations here, and it'll take a little bit of time, but after 5,000 iterations, let's see how far it got, and it's pretty good here. Okay, slope is at 7.985 and my intercept is at negative 400. We can compare this to the linear model, which is at 7.989 and negative 400.389. Okay, so probably if I did another 1,000 iterations or so, it'd probably get there. I mean, we have the computer and it works really quickly, so it's not too much of a problem for us. But let's see. Okay, it's right there at for the slopes, negative 7.989, right? So we could do model $ coefficients. Okay, so what do we have? 7.989381. Okay, so it's pretty darn close. And then if we ask what our intercept is, 400.3874. Okay, so our algorithm is getting there, but it took us 10,000 iterations to get there. Okay, so there are limitations, or there are applications of coordinate descent where it doesn't work as nicely. Okay, and those would be cases where the contour is this really kind of this thing where you're going to have to take a ton of tiny little steps to get there. Okay, whereas if you have this nice circular thing, it's going to coordinate descent will get there very quickly. Okay, so I hope that clears up or sheds some insight on just what's happening when you're doing the homework. I tried to explain what's happening in the homework also, but that's what this thing does. Okay, so we'll end there, and we'll see you guys on Wednesday. And don't forget to vote if you're gonna vote. So.